So, hello everyone. Welcome to today's Future Intelligence Talk session. We are excited to invite Dr. Wang from Texas A&M University from the USA. Today, her topic is about enabling human-robot partnership for digitally driven construction. Let me give you a brief introduction about Xi. She is an assistant professor in the Department of Construction Science at Texas A&M University. Her research focuses on the intersection of robotics, human, and infrastructure to create a much safer, more productive, and comfortable construction and building environment. Her research interests include human-robot interaction, multi-robot coordination, robot and infrastructure intelligence, and human factors interacting with intelligent agents. Before joining the University of Texas A&M, she obtained her PhD in civil engineering from the Department of Civil and Environmental Engineering at the University of Michigan. So it's your time, Xi. Thank you.
Thank you. I will share my screen. You can see my slides, right?
Yes.
Yeah. So, hello everyone. Thank you for coming to this presentation today. I will introduce my research about enabling human-robot partnerships for digitally driven construction. And this is the outline of my presentation today. I will start with the background by discussing the vision and challenges for robotic construction, followed by the overarching goal of this research. And then I will introduce the closed-loop beam-driven digital twin system as the study, and I will conclude this by briefly summarize this research. So first, I'll start with the background. The construction industry is facing several issues. So it has high physical demand on its workers. It often requires workers to carry around very heavy objects, and in many cases, they need to bring it overhead for a while. So many workers are facing work-related musculoskeletal disorder issues. And while many other industries have experienced significant productivity growth in the past few decades, the productivity of the construction industry is relatively stagnant. And the work environment, the construction site is dangerous and hazardous. The workforce is male-dominated. And partially because of these reasons above, the industry is now also facing severe labor shortage. That the young generation and are reluctant to choose construction as their career, and female and people with physical disabilities are hard to find their positions in the industry. So how can we solve this, and what can we do to make it better? A promising solution is robots. The robots has high speed, great physical power, and it can accurately repeat the work without getting tired. So it has high potential to mitigate these issues faced by the construction sector. However, until nowadays, very few robots can be found on construction sites. So to understand the reason, we can take a look at of human and robot capabilities. So the humans are creative and they can adapt and adjust based on the instantaneous scenarios. They are good at perceptual understanding and learning from past experience. Well, for the robot, it's difficult for the robot to produce truly innovative ideas or concepts, and it is challenging for them to adjust to new scenarios that fall outside their predefined operational protocols or training data. In this case, human improvisation and intervention are often required to cope with such changes. And the robot have low synthesizing ability to combine various sources of information, and they often lack the instinctive understanding, or we can say gut feeling, that humans often rely on for decision making. On the other hand, the robot has high physical capability, and they can detect the minor deviations in the physical world and perform fast numerical computation. and they can perform work with high speed and accuracy. Well, compared to these robot capabilities, human physical capability is relatively low, and we cannot detect the minor deviations like a few millimeter or centimeter deviations in the physical world is hard for us to tell by our eyes. And our performance is often inconsistent and subject to errors. So from this, we can see that some human capabilities are indispensable for construction work and are hard for robot to possess within a short period of time. So human-robot collaboration that take advantage of both humans and robot capabilities is emerging as a promising approach in the area of construction robots. So for any of human-robot collaboration tasks, we can consider it from a vector of three capabilities. The planning, that is the high-level operational planning capability. Cognitive, that is the low-level execution planning, like the trajectory or motion planning. And physical task performing. So for the most current human-robot collaboration tasks, the robot performs the physical work and a human performs most of the planning and cognitive work. So it can greatly reduce the physical stress of construction workers by relieving them from strenuous physical construction activities. But the robot capability is limited to the physical work that cannot or is difficult to be pre-programmed or fully autonomously performed by the robot because of the complexity of construction. So we propose that human-robot collaboration should make better use of robot intelligence by letting robots perform some of the planning and cognitive work. And in this case, both the physical stress and mental effort of the construction workers can be reduced, and the overall productivity and safety of the human-robot work team can be improved. So with this vision, it leads to the overarching goal of my research is to create a system to enable smooth human-robot collaborative construction. And I worked towards this through three steps. First, I developed a collaboration platform that allows humans to remotely collaborate with robots from a safe work environment. And at the next step, I integrated building information modeling as an additional database to improve the accuracy and autonomy of the system. And finally, I explored how to let the robot learn motion sequencing skills from human to further reduce human planning effort. And for the time reason for this talk, I will focus on the first two objectives. So the first objective is to establish a collaboration platform that allows humans from a safe workplace to remotely collaborate with on-site robots, with humans perform high-level planning and supervision work like a supervisor, and the robot perform sensing, cognitive, and execution of the work as an intelligent assistant of humans on the construction site. So what technology can help us establish this collaboration platform? The first thing that came into my mind is digital twin. So the digital twin is a virtual replica of its original entity, and different from 3D models or 3D simulations. The digital twin can communicate with and exchange data with the physical world. And it can also gather data from different sources like database or cloud-based platform. So overall, it allows connection, visualization, and interaction, and makes it a good candidate for as the basis to develop this collaboration platform. So with this vision, I proposed an immersive and interactive process-level digital twin system. The system contains three modules. So on the human side, we have an immersive VR interface that creates an augmented telepresence experience to the human workers and allow them to support their planning, instruction, and supervision. And on the robot side, we also have the robot operational environment that includes the construction site, the robot on site, and the sensors either on site or on the robot. So it can perceive construction site environment, detect robot states, and is also where construction tasks are actually executed. So to connect human and the robot and the construction site, we introduced the robot operating system as the middleware. So robots can not only wirelessly communicate with both the VR interface and the robot by sending and receiving different messages, but it can also perform computation work like sensor fusion, motion planning, and robot control. So as the next step, for our next objective, I integrate building information model into the previous system. So building information model is the technology widely used in construction that it contains not only the 3D geometry of the building, but also the information of each components in the building. So by integrate BIM into the system, it can provide the data to both humans and robots to drive the construction process and make it more accurate and automated. Also, the as-built information collected by the robot can be sent back and to be recorded in the BIM for future use and close the loop. So I propose a 4-step BIM-driven construction process. So the first step is to create a BIM that can be used both by the human and the robot. And then we need to do some preparation on site. And then comes the construction process. And finally, after the construction, the as-built data will be updated in the BIM. So I will then delve deeper into each of these steps. So the first step is BIM creation. So BIM is playing an increasingly important role in the industry, all the way from the design phase to the operation and maintenance phase of the building. However, it is not originally designed to support robotic construction. So here the question is, what should BIM be like? What information does BIM need to contain for robotic construction? And how can we take advantage of the existing platform to enable this connection? So first, BIM need to have the shop drawing geometry that instead of an entire wall surface, the robot need to know where each panel goes. And the second is, since in construction, we have loose tolerance that we design the frame to be installed at this place, but on the construction side, we may have some uncertainties, some situations that we finally decide to move it a little bit, but this may cause confusions on the robot. So this object relationship can help solve this issue. So in this case, the frame is a parent of those panels. So if the frame is deviated, the robot knows that the panel should go with the frame and it need to adjust the installment of the panels according to the frame location. And a clearly defined layer and type can make it easier for robot planning and control. And the BIM can also contain the sequence data to automate the construction process. And lastly, especially for some construction materials with irregular shape, we need to tell the robot how it should grab the object, like give it the position and orientation to grab the object. So in this study, although I manually input many of this information, several of this information has high potential or has already been able to be automatically generated. So for example, we can transfer the beam component into shop drawing geometry, and we can automatically figure out the sequence to install objects, or we can let the robot automatically decide how it should grab the object. And after we create the beam, we come into the next step to do some preparation work for construction. So this includes to switch on the sensors on the robots, to prepare the materials, place them into the robot workspace, and lastly, to assign tasks to the robot in the beam. So the beam has relatively, compared to the robot, has relatively user-friendly interface. So the workers can just select to choose a few objects in the beam and place it onto the target layer. In this way, the worker is telling the robot, I want you to install this these few work pieces or objects during this task. So after preparation, we can start the construction. And to begin the construction, the digital twin needs to be generated. So here I propose the automated approach to generate the digital twin. The beam is saved in Rhino, and then we created the connection interface in Grasshopper to retrieve the information from the beam and publish it to other modules in the system. There are actually two digital twins of the beam in the system. The first one is in the interaction module in Unity. So you can see that through one click on the button in Grasshopper, the digital twin interface is generated in Unity, and it is interactive and it's ready to use. So we use some template to attach the interactive functions to these objects. And the second digital twin is the computation module in robot operating system. So it is used for the robot to do some planning work like collision detection during motion planning. And after the beam is generated, another issue we need to consider for construction, as I mentioned before, is the potential deviations. And that happens a lot on construction sites. So we consider two situations here. The first is the parent of the object I want to install is deviated. And the second situation is the nearby objects is deviated. So we propose two solutions for this. One option is that the robot can automatically suggest some new installation posts for human to check and approve. Or the user, the human, may choose to directly replace the material with different shape or smaller size to fit the deviation. So for example, for the parent deviation here, the robot can use the as-built transformation it detected from its sensors. And the as-designed transformation, it extracted from the beam to calculate the design-built deviation. That is how the built geometry is deviated from the design. And then it can suggest, based on this transformation, suggest new installation posts to install the construction material. And it can visualize the suggestion to the in the interface to humans to let the humans to approve it or make manual adjustments to the suggestion. And the last part is about the data transmission for the physical robot system. So we have the beam and VR interface usually on the Windows platform on the PC, and we have some sensors connected to microcontrollers. So both of them can communicate with the computing core in the robot operating system. And when the computing core decides to control the robot, it will send the joint states through ADS bridge to the robot embedded PC. And then the joint states will be sent to the robot to control the robot movement. So here's the demonstration of the study. So at first, the robot only know where the frame is designed, and they don't know where the materials are placed because we just place it on the side. So first, it moves its camera to scan the environment to find out the actual frame location and the material location. So you can see that for the frame, it's almost impossible for us to place it exactly at its design location during the experiment. So there are some deviations and it's showing in red. And the materials are detected and showing in yellow here. Then the robot will suggest new installation posts and the human can approve it. After approval, the robot can generate the motion plan and the human can preview this plan in the interface. This is because the construction robots very often have very high payload and have strong physical capability. So it's sometimes we feel uncomfortable that we don't know what the robot is going to do and directly let it execute the task. So with this, we kind of get an idea what the robot wants to do. And after we approve it, the robot will follow exactly the same plan to execute the task. So in that way, if you don't know what the robot is going to do, it can be the human workers can be stressful to work with huge size robot. And in this way, we have better check of the robot. And after one workpiece is installed, the robot will check for the next workpiece in the system, follow the process of make suggestions and generate the motion plan. So you can see that sometimes the robot has a lot of rotations, and in that way, we want the robot to generate another plan. So we avoid the process of rotate this heavy wall panel several times. So in this case, this plan is much better. So robot can execute it. And after the tasks are finished or reach some checkpoint, we can then further update the beam with the information we collected. So in this case, we have the workplace sensing data, that is the frame, the attribute location of the frame. We have the robotic construction data, that is where they installed the panel. And lastly, the material data, that what materials, how many of them, and where they are left on the construction site can also be updated in BIM. So to conclude, this study proposed a human-robot building connected framework for collaborative construction. For the first objective, we developed an interface, digital twin interface with inspection, planning, supervision, and execution functions to reduce human physical and cognitive effort. And for the second objective, we further improve the accuracy of the human-robot collaborative construction and reduce human planning effort by integrating building information model into the framework. And we also explore the system setup for the physical construction work. And most importantly, this is an evolving framework that supports some future research opportunities or flexibility that the other researchers or professions can replace the modules like the object detection or the robot motion planning modules in this framework and use connected with other modules to explore the whole construction process with the improved algorithm they proposed. So lastly, I want to acknowledge the financial support of this research from the U.S. National Science Foundation and from by the fellowship and scholarship from the Rackham Graduate School and Department of Civil and Environmental Engineering from the University of Michigan. And here are the references, and I'm open for questions.
Okay, I think it's a very, very good presentation, a very, very interesting research. Okay, and is anyone from the audience have questions? Please raise your hand, please. Okay, since people are maybe still thinking of questions, let me possibly ask you a first question. So I saw the main concept of this is the physical and digital interaction, right? You mentioned that for this framework, you transfer some of the planning effort from human to robot. Like you mentioned that the robot will be equipped with sensors and cognition. So I was just wondering, what kind of the cognition does the robot have, right? Is this about motion planning or recognition of some objects?
Yeah,
What?
it is mainly about motion planning because we
Okay.
also consider teleoperation that is very popular as well.
Yeah,
But
exactly.
but for the relatively large workpiece like wall panels, it is a little bit challenging for human to operate the robot and decide the collision-free path. But with robot, when it knows the objects nearby, it can better generate a collision-free motion plan based on the collision scene. So we allocate this task or this cognitive activities to the robot for it to do the computing.
But I'm aware that I don't know whether this your framework is required human to be present nearby the robot or not, because we still want to remove the human out of the work site, right? And
Yeah,
human can sit alone in the office, and then watch robot to work. But
yeah.
that also possible, right? With your framework.
Yeah, that is possible, but actually, at least when we do the experiment, we are not allowed to enter the robot workspace because for the safety reason we can't go inside, but we kind of stay nearby to monitor the experiment process, and we also need to bring some materials into the workspace. So the intention is at least not let the workers stay in the robot workplace, and we also the framework also support remote collaboration, but still some workers need to place the materials in the room of the robot for the robot to perform the subsequent work.
Okay.
Hi, Jerry.
Hello. Yeah.
I have a question.
Okay. Yeah. Please.
Yes, thank you, C, for your presentation. And I'm Muda. I'm a research associate in the Cambridge, and I am working on the scan to beam, meaning from the point cloud to the as-built beam model generation. So I want to ask, in your project, you have integrated as design beam and also as built beam in the framework, and I want to know how the as-built beam are integrated in the and help the robot to operate. Like is from the image, or you use because there is a sensor on the robot, so it's for the point cloud collection or image collection for the as-built beam generation.
Yeah, so in our case, we didn't use point cloud. We just used the tags, the fiducial markers for the robot to detect the frame and the material locations. Because in our framework, we want to focus on the implement the whole integration process. So we didn't specifically focus on how the object is detected. So we have several ways that can detect the object, like the point cloud. And we may also rely on your research like to scan to beam that can also be helpful. But since the scope of the study is not on the reconstruction or object detection, so we just use some existing method like fiducial markers. But of course, this has some limitations, like we need to deploy the markers. But for the research demonstration purpose, we just use these markers, and we hope that there can be some other easy to implement technology that can help us understand the environment and get the as-built beam.
Okay, thank you. Yeah, because I just want to explore how maybe we can have some future collaboration on this area, because this can maybe be beneficial for this project.
Yeah.
Yeah, thank you.
Thank you.
Okay. Want anyone have other questions? We probably having another question. Okay.
I have, my name is Alvin. I am a research associate in Cambridge. I want to know how the robot is transported from one place to another, because I think the reach of the robot is limited, and as a ongoing construction building, moving things as big as a robot will be very difficult. What's your thought?
Yeah. So in our case, we use the relatively large robot. So I think the reaching is about 2.5 meter, and the payload is about 120 kilogram. But in actual construction project, using this size robot can be very challenging. That it requires relatively large, high bay roof, relatively large area, and a strong floor to support this type of robot. And I think in the future, maybe using a few smaller robots to collaboratively do the work is more promising, can have better potential for the practice.
Thank you.
Okay. regarding the time, I think I have to announce that our session today is going to end. And yeah, thanks again very much again for this very interesting presentation. We hope to reconnect each other in the future. Yeah, and all the best to your career and research. Thank you very much.
Thank you so much for your invitation.
Bye bye.
Bye.